So we are in the lecture of ANOVA, and now it is the turn of two-way ANOVA. So the problem is we have a continuous output variable, so it is a regression problem, and we have two predictors that are made of categorical variables or discrete input variables. So let's say that we have x1, x2, each one with labels, and then for each combination of the labels, for instance, we have by, by. So for each combination we have different values. So if now you compute the combination by, that is this column here, so we have a number of observations and the same for the rest of combinations. So we want to compute for every pair of input variables what is the expected y value. So the expectation or the observations that we have for y at a particular x1, x2 that we will encode as xi, xj will be an overall mean plus the contribution of the first factor, so x1, that is contributing with the level I, plus the contribution of the second factor x2 that is contributing with the level j, and some residuals. And as always in regression, the residuals will be assumed to be Gaussianly distributed with zero mean and fixed variance. So as we did in the one-way ANOVA, we will constrain our model so that it is unique, and then we will impose the condition that the sum of all the alpha i's have to be 0 and the sum of all the beta j's have to be 0 too. So then we have these observations, and then we have the overall mean, and then for each combination we have a contribution coming from x1 and a contribution coming from x2, and the addition of all these contributions have to be 0. The addition of all these contributions have to be 0. So at the end, this model of mu plus alpha I plus beta j, what allows us is to deform this constant plane into something that adapts better to the observations. Then we can further complicate the model by introducing something that are called the interactions. So that is combinations of or observations of y that cannot be explained alone by alpha and beta. So this particular combination is particularly good or particularly bad, and then we add another set of parameters that are the theta ij, that are the synergies between factors, and as always we also have to constrain them. So the constraint is that the sum for all i's of the theta ij's have to be 0. The sum of for all j's of the theta ij's, they also have to be 0. So now the model would be something like that. So we have a constant plus something that depends on x1 plus something that depends on x2 plus something that depends on the combination of x1 and x2, and then we can further adapt these irregularities of this plane, of this surface, to the observations that we have. Then we can count the number of parameters that we need. So here we have said we need 6 coefficients. So we need 1 for the mean. We have 4 levels for alpha, but we know that we only need to compute 3 because the 4th is automatically determined. So we have 1 plus 3 plus 2 for beta, and the reason is that the third beta again is automatically determined. So we have 1 plus 3 plus 2, that makes 6. Then if we have this configuration, we have 1 plus 3 plus 2 because we have to estimate the same mean alphas and betas. But now, instead of having to estimate 12 coefficients, that is 4 times 3 for x1, for the interactions of x1, x2, actually because of these constraints, that the addition for all i's and the additions for all j's have to be 0, that is imposing a lot of constraints. So actually the number of parameters we need to estimate is x1 minus 1 times x2 minus 2. So in x2 we have 3, so minus 1 is 2. In x1 we have 4, minus 1 is 3, 3 times 2 is 6. So for estimating the interactions we only need 6 numbers, plus the 6 numbers that we already had for the mean, the alphas and the betas. So in total, fitting this kind of models, it is relatively cheap, especially the interactions. The interactions are pretty cheap, and they can bring a lot of flexibility to adapt to the surface. And later we will see that we can check whether the interactions are really present or not. So as with the one-way ANOVA, we can compute the two-way ANOVA table, and the interpretation is the same. So it is for every factor that we are analyzing, x1, x2, or x1, x2, and the interactions, we compare the mean squares of that contribution compared to the mean squares of the residuals. So the mean squares of the residuals in this example is 97, 99, or almost 100 here. And then we can compute an f, and from this f we can compute the p-value. So let's see this with some examples. So let's say that we have 100 observations, and these are the alphas, these are the betas. So the alphas are not all of them are equal, the same for the betas, not all of them are equal, and then the standard deviation of the noise is 1.5, and the mu is 2. Okay, so here we have our observations, and when we do the analysis, the ANOVA, the two-way ANOVA, what we see is the following. So x1 is very significant, x2 is very significant, and the residuals, the mean square of the residuals is 1.7, the truth was 1.5. This is a good estimate given that we only have 100 observations. So we had different alphas, we had different betas, and the two-way ANOVA has been able to identify them. Now we have the same alphas and betas, but we have much less, many less of observations. Even there are combinations for which we don't have any observation. We see A set, for instance, doesn't have any observation. Y, dy also doesn't have. And then now we don't have enough evidence to show that x1 and x2 have different alphas and betas. So the p-value is not significant, and they were really, in reality they were, but because we don't have enough evidence, we cannot show that the alphas and betas are really different from each other. So now we have all the alphas are the same, the betas are not. We have a lot of data, and now what we see is that x1 is not significant because there is no difference between the alphas, and x2 is significant because there are differences between betas, and the two-way ANOVA was able to identify this situation. Now we introduce the interactions. So now the interactions, they're all zeros except one of them that is different from 0. The alphas are different, the betas are different, and now the p-values, or the 3 p-values, are significantly smaller than this threshold of 0.05. So all the 3 contributions are present. Now we don't have any interactions. We have alphas and betas, but we don't have interactions. And then, but let's say that, let's pretend that we don't know that. So we do the analysis, including the interactions term, but now the interactions are not significant. So we see that the two-way ANOVA is a rather useful and powerful technique to identify the different contributions of different factors. So this would be all for the ANOVA lecture, and see you next time.